But of course, I can as well keep these notations quite generic, just h0 and h int, and you can easily believe that if it's some other field theory with some other h0 and h int, whatever we are doing will also go through there. Now, the key property is that h0 describes the free theory, and the free theory can be solved because we know the Hamiltonian and its diagonal, and we know all the eigenvalues, and we have all the machinery to calculate anything. For example, if I put a product of phi's inside a vacuum expectation value in the free theory, one thing you can do, may not be the easiest one, is just take all the integrals out. Phi's, as you know, are integral d3k of a's and a daggers. Take all the integrals out and you have a bunch of a's and a daggers. Okay, given any bunch of a and a dagger, you can always commute them through each other till all the a's come to the right, all the a daggers come to the left, and then you get 0. So you pick up all the commutation terms, and that's your answer. So this you should be very sure about. In this theory, we can calculate for example, using oscillators. We'll see that there are much easier ways of calculating this quantity without using oscillators. In fact, of calculating the quantity of interest to us, which is typically not this, but the time ordered version. But if you know this, then of course you also know the time ordered version, because you can put this into the expression for time ordered function, and you can always use oscillators, however painful it is, to calculate the answer. Is it very clear to everybody that you can use oscillators to calculate this in a free theory? We did the example of phi x1, phi x2. We called it d of x1 minus x2, and we did it last time. It really doesn't change anything if you have 3 or 4 or 10 fields in this. Okay. The difficulty is this one. The interaction no longer allows you to do that. Okay. And so our goal is to express interacting QFT quantities in terms of free QFT. If we can do this, then at the next step we can use this fact that in the free theory everything can be calculated. Okay? And this expressing of interacting QFT in terms of free QFT quantities will be done via perturbation theory. Which means we treat this interaction as a small perturbation to the free theory. Now supposing at some instant I start with a field configuration at some instant t equals 0, then we know that the evolution of this field is always given by the Hamiltonian with a plus sign on the left side and minus on the right side. This is the field of physical interest, but it's not a free field, because H is not a free Hamiltonian, because H is H0 plus H int. Okay? However, I can also define a free field which I call phi 0 of t and x. Sometimes in the book this is called phi I, and it's referred to as the interaction picture field. I can define it by taking the evolution of the same configuration using the free Hamiltonian instead of the full Hamiltonian. Okay? So, at any time, I have available to me two fields, one which is the true interacting field this one, and this one is a free field called the interaction picture field. And our goal is to express physical quantities that are defined through this in terms of this, and then use free field theory to calculate the quantities in terms of this. And by the end of this lecture, we will have a nice formula which says, given any quantity that you want to calculate involving this, I'll give you the quantity which you need to calculate involving this, and it'll give you the correct answer. However, what you will calculate in terms of this will be very hard to calculate, and you'll only be able to do it order by order in lambda. Okay? And that's a price you have to pay. But whatever it is, since in many physical systems and many genuine systems like electrodynamics, the corresponding coupling is in fact small, we can use this procedure and get very good, very accurate answers. Yeah. No. On the RA, it's the same field. So imagine that I have a field configuration at a particular time. Okay. One way, if you want physically to think about it, is imagine the interaction got switched on at t equals 0. Okay. Then the field configuration, whatever it is, will evolve in this way if we evolve it using the free Hamiltonian, and the same configuration will evolve in this way if we evolve it using the interacting Hamiltonian. Okay. Now, last time we also defined the vacuum 0, which satisfies this. Of course, this is the free vacuum, and it's gives me the zero energy eigenvalue of the free Hamiltonian. Of course, this I got by subtracting that infinite constant, but that we have already done once and for all. What about the interacting vacuum? Now we can't guarantee that the minimum energy is 0, because just think of perturbation theory. In the unperturbed system, we have a ground state energy. In the perturbed system, we'll have a different ground state energy, and we don't know what it is. It may or may not be physical, but it will be some different number. So I should just call it E naught. And this is the interacting vacuum. That means the vacuum of the interacting system, while this one is the free vacuum. So these are all completely natural concepts. We'll see in a moment that this interacting vacuum can be expressed in terms of the free vacuum, again in perturbation theory. Okay, now combining the formula in the middle, I can get a relation between the interacting field phi of t and x and the interaction picture field, which is a free field, phi 0, by simply taking this relation and then solving for this middle piece, phi of 0 and x, using the second line in terms of phi 0 of t and x. So I get e to the I h t, e to the minus I h naught t, phi naught of t and x, e to the I h naught t, e to the minus I h t. Okay? I hope this is clear. It just comes from that pair of equations. And this can be written u of t, phi naught of t and x, u dagger of t, where u is a unitary operator defined as so what's the physical meaning of this? Sorry, I think it's the other way around. Don't write as yet. Yeah, it's the other way around. So it's u dagger, and here is u. So u is whatever is on the right side. Okay? So what's the physical interpretation of this formula? It says, at a fixed time, the free field can be converted to the interacting field by some operator u. Is the operator which converts the free field by conjugating it from both sides, converts it into the interacting field. Okay, so clearly knowledge of this operator is all important. This is what contains the information about the interaction. And if you look at this form, you can see that it does, because H is H naught plus H interaction. So this depends on both H naught and H interaction. And it would have been very nice and very easy if the operator H and the operator H naught commuted. This e to the I H naught t, this is e to the minus I H naught plus H int times t, and then we would like to perhaps cancel these two factors, and it would be just e to the minus H int t, but this is wrong. Why is it wrong? Because we have H naught and H int in the exponential, and we cannot write e to the H naught plus H int as e to the H naught times e to the H int. So e to the minus I H naught plus H int t is not equal to this product. Why? H naught and H int, thank you, are both operators. Okay, the whole point is we write exponentials very cheerfully as if they are the most natural thing in the world, but what we really know is e to the x, where x is a real variable. Here we have written e to the h, where h is an operator. In fact, at some point one should stop and reflect what is the meaning of this. Okay, because it's not a function and it's not a number, it's an operator, but the meaning is nothing more nor less than saying e to this quantity is 1 plus this squared plus this cubed upon 3 factorial, etc. Power series expansion of exponential. That you can do, and even if it's an operator, the power of an operator is perfectly sensible. It means act with that operator many times. So this is defined as a power series, this is defined as a power series, and this is also defined as a power series with h naught plus h int. Okay? Now you can compare the power series for this and the power series for this, and you'll see that in this one there will be many terms involving h naught and h int on different sides of each other. Okay? But h naught commutator h int is certainly not 0, because look at their form, they're gone from here. H naught was that summation alpha dagger alpha type of thing, and h int was phi to the fourth. So it had alpha to the fourth, alpha dagger to the fourth, all possible fourth powers of alpha and alpha dagger. That doesn't commute with summation alpha dagger alpha, right? People looking very puzzled. Because, alpha, sorry, A, yes, I did some mental flip. A dagger A, yeah, A and A dagger, since they don't commute, this is A dagger A, and this is fourth powers of A and A dagger, they certainly won't commute. Because they don't commute, this is not equal to this. Okay, so what do we do? Is to obtain a differential equation for u of t, and then integrate it back, being careful at all times that we never assume h0 and h int to be commuting. So the differential equation is obtained by simply acting with d by dt on u, and u is defined by this. Now let's be very careful and ask what is d by dt on this. So d by dt, these are two factors. So d by dt we can certainly distribute, acts first on this factor, second on that factor. When it acts on this, it actually pulls down IH0. Okay? Why is that okay even though H is an operator? Because H0 commutes with itself. Okay? So I can pull down IH0 and it doesn't even matter whether I write it on the left or right of this exponential, but it shouldn't go through this one. It's not allowed to go through that one. So it's IH0 and what's left is still U. After bringing down IH0, I get back U. Then there's another term when the d by dt acts here. In this one, H comes down, but it's not allowed to come to the left. Okay, I could keep it on the right. So minus I U H. Okay, and it would not have been correct to write minus I H U. Because d by dt acts on this. This H, when it comes down, I can put it here, that's allowed, or I can put it even here, but I certainly can't put it on the left. So this I can write most conveniently as follows. Since U is e to the IH naught t, I can separate it into its two parts and put H naught minus H in the middle. This I am allowed to do. What did I do? I took U, which is the product of these two things. H naught can go through the first term on the right side. Here H is allowed to go through the second term and come on the left. So only in the middle they are allowed to meet each other. So this is a correct statement that du by dt is this. Is it clear why? To get this result, I have taken down H naught from here, but I have not taken it through the second factor, and I have taken down H from here, but I have not brought it through the first factor. So it's legal to put them in the middle, so this is the answer. Okay. Now, I've got something that I like, because this quantity in the middle has a name. What is it? This is H interaction, or minus of it. So let me check my signs carefully. Yes, it's a minus of H interaction. So this. In the last step, I write this as e to the IH naught t, H interaction, e to the minus IH naught t, and then so I introduced a pair of e to the minus IH naught t, e to the plus H naught t. Okay. Now what's the advantage of this? What's the last term? It's just u again. So du by dt is something which I know times u. That's the equation. So let's define, and then we'll understand its physical meaning in a moment. Hi of t to be the first factor, then the differential equation is I du by dt is Hi times u. This whole thing is Hi. This factor minus I took on the other side, and this is u. So I get a relatively simple looking equation. What's the physical meaning of H capital I? It's called the interaction picture Hamiltonian. That's the name. What it means physically is, it's the interaction Hamiltonian H int, which is phi to the 4, evolved in time by the operator which evolves the free field. Okay? And it's not surprising that this will be the building block of our answers, because all our answers involve free fields only. So here's the equation. Everything depends on t and only t. Right? So I want to integrate this equation. So how do I do that? If I integrate this equation, then I've got u. Separation of variables. There's only one variable. What variables should I separate? That way. du by u and hit. Very good. That's close, but it's not completely right. So let's decide whether it's right or not. So the suggestion was, but it's good, you should always start with something. Suggestion was, imagine taking u on this side, so du by u, and here we get h times dt. Okay, so suggestion is, if we follow this, we'll find u of t is e to the minus I integral h of t prime up to t. Yes? That's what you would get if you solved that in the way that was suggested. Now, what could possibly be a problem with this? No. H is time dependent. That's perfectly fine. Hi is time dependent. It's the interaction picture Hamiltonian, and it evolves from the interaction Hamiltonian by the time evolution operator of the free theory. So it's time dependent. They are operators, yes. Yeah, that's certainly one thing, but I wouldn't be too worried about u of t being 0 because it's a unitary operator. Unitary operator can never be 0. U dagger u is 1. Huh? Yeah, that's true, but u dagger u is 1, you agree, right? So then if u dagger u is always 1, then u cannot become 0. So that's not a worry. But you also said that it's an operator. So what is exactly the manipulation which led to this? That's correct. It's an operator multiplying another operator. See, there's no problem integrating an operator equation like a normal equation as long as the different operators commute, or otherwise you take care of the fact that they don't commute. Okay. Now the key result here is that hi at t and hi at t prime do not commute. This operator hi is a time dependent operator, it's a time evolving operator, but at any time it doesn't commute with the operator at any other time. That's just built in, you can use the definition on top and check. And that's inherited from the fact that h0 and hint fail to commute. Because of that, this is also true. And now you see a problem. The best way to see the problem is, look at this and let's guess let's guess this as the answer and try to see if it solves that equation. When you have a simple differential equation, it's good to guess the answer. This is a guess. It's actually very close to the correct answer. Now let's use it and see if it solves that equation. So let me take du by dt. Now what should I do here? Yeah, but that's the problem. So okay, good. So d by dt, 1 minus I integral. So I'll write integral h as shorthand for integral of h t prime dt prime up to t. Hi. Thank you. Thank you. And here's t. Okay. Now, probably from the third term, They are the same t. The argument here is not the same. This is a dummy variable. This is the same t. I am expanding one quantity, right? Okay. I forgot to say that the lower limit is 0. That's very clear from the fact that what is u of 0? U of 0 is 1. We know that from the definition. Because u is this, right? So if I put t equals 0, I get 1. So the lower limit is 0. So that, but it's the same t. This is h of t prime dt prime up to t. This is h of t double prime dt double prime also up to t. And this is h of t triple prime dt triple prime up to t. All different integration variables. But the upper limit is the same for all. Okay. Now you start seeing the problem. When d by dt acts, for example on this term, it will give me h times two integrals plus integral times h times integral plus integral times h. Now you see those three are not all equal to each other. You see that? Because h at t and h at t prime don't commute, this doesn't give me the right answer. And this is something that you should certainly go through in tutorials. Even here, if I differentiate this term, the first term gives me hi evaluated at t times the integral. Another term gives me hi evaluated at t times the integral from the left. But integral of h and h itself at a time t, these don't commute because the integral contains the value of h at all possible times. And h at the last time t will not commute with h at all the previous times. So this is a problem. So let's give a solution. It's a very pretty solution. The solution is got by putting a familiar symbol outside the right hand side, and it's the time ordering symbol, t of that. We've already encountered t. What time ordering does is to impose a fixed ordering on all the operators inside it, such that all the ones at later time are to the left of those at earlier times. Okay? Let's give a very concrete illustration by discretizing the time. So let's assume that 0 to t h of t prime dt prime is actually h at 0, I'm putting it as superscript, plus h at 1 at epsilon plus. You understand what I've done? When there's an integral, we divide this range 0 to t into small pieces, 0 to epsilon, epsilon to 2 epsilon, 2 epsilon to 3 epsilon, like that. And basically an integral is nothing but a sum over all those. Into epsilon. Okay, like this. Now, consider the ordinary exponential of this quantity and then consider the time ordered exponential. And once you see the difference between those, everything will be clear. The ordinary exponential, this is all hi, The ordinary exponential means e to the minus I epsilon h at 0 plus h at epsilon plus h at the final time t. Okay? And here is an exponential of many quantities, all of which fail to commute with each other. On the other hand, t of this follows a very simple rule. It says, first look at the earliest time h naught. Write e to the minus I h naught epsilon here on the rightmost point. Next, write e to the minus I h epsilon times epsilon. Next, write e to the minus I h of, sorry, these are here. This is not that h naught. And here, h at time t times epsilon. You see the difference between these two expressions clearly? And you can see that if h was not an operator, of course there would be the same expression. Because h is an operator, to convert this to this requires all possible commutations between all of them, and all are non-zero. So this is the version where all are added in the exponent, and this is the version where all are multiplied after exponentiating each one. Now if I take a continuous limit of that, where this epsilon tends to 0 and number of intervals tends to infinity, I recover the integral. If I take a continuous limit of this, which is harder a little bit to imagine, I recover by definition time-ordered exponential of integral. It's a very nice trick that can be used with operators in many areas of quantum mechanics, not only here. Okay? Now see why this is good. In the first one, if I differentiate with respect to h, if I differentiate with respect to t, I would pull out this h. But I wouldn't know what to do with it because it's up there. In the second one, what do I get if I differentiate with respect to t? I just pull out this h nicely on the left. That's the equation I'm trying to solve. Where did the equation go? It vanished. The equation says I du by dt is hi at t, u at t. So when I differentiate, I would like to have the hi at t come on the left of everything. In this form, it's already on the left of everything. In this form, it's jumbled up with everybody else. That's the key difference. So in this form, it's very clear that this solves, therefore time ordering correctly solves the original equation. And if you want more practice with time ordering, then I think you should do that in the tutorials. So I'll continue assuming this to be the solution. Now let's ask ourselves, what is u dagger of t? What should it be? We'll need that also. Under dagger, what happens to I, the factor of I up there? Changes sign. What happens to the h? H is Hermitian surely, it's a Hamiltonian, it's even a term in the Hamiltonian, it should be Hermitian. But there's one more subtlety. Okay, the time ordering turns into reverse time ordering. Because remember, when you take if you have matrices A and B and you take the dagger, you get B dagger, A dagger, right? Reverse order. Not the same order. Same thing is true here. So this is T bar e to the I. And now let's convince ourselves that this is correct. If I multiply these two, what happens? Is it clear that I get 1 only because of this T bar? This is anti-time ordering. Anti means the latest time on the right. So why is this? If I multiply in this order, u and then u dagger, this one has t equals 0 on the left and this has t equals 0 on the right. So the corresponding terms just cancel each other. E to the minus I h naught, the other one has e to the plus I h naught over here. After that, stepwise they keep cancelling until everything is cancelled. If you multiply in the reverse order, also it's true. Because then u dagger with anti-time ordering has the latest time on the right and this has the latest time on the left. So they again keep cancelling and you both ways, so you get u dagger equals u dagger u equals 1. Not only that, very beautiful identity, which we'll make use of heavily later. Imagine u at t1 and u dagger at t2, where t1 is greater than t2. Can you guess what this should be? This one is time ordered e to the minus I integral 0 to t1 of hi, and this one is time ordered integral anti-time ordered e to the I 0 to t2 hi. Now this one, just look at it, the time goes from 0 to t1, but on the way it passes through t2. t2 is an earlier time than t1. So this one is the same as time ordered e to the minus I t2 to t1 times time ordered e to the minus I 0 to t2. Is that clear? Because the time ordering prescription puts all the later times on the left. So if we break up this interval into two pieces, we can extract a separate time ordering symbol for this one and for this one. Because this arranges all these times from 0 to t2 this way, and then this arranges them from t2 to t1 this way. So it's the same as what we had before. But now if I multiply with this, then these two of course cancel each other because they are dagger of each other, and I'm left with the nice result that u of t1, u dagger of t2 is this quantity, which I can give the name u of t1 comma t2. Is the integral from t1 to t2 of hi. But remember, this is only true for t2 greater than t1. If t2 was less than, t1 greater than t2. If t1 was less than t2, then this manipulation would fail. So this is a very useful relation, that there is a u with two arguments, which is the exponential integral from t1 to t2 time ordered. Okay. So by now you are thoroughly tired of these manipulations and you want to see what use they are. Omega, the true vacuum, time ordered product of phi at x1, phi at x2, 0. Omega. This is what we could call the full propagator. Whatever formula I end up with, without proof I'll extend it to the case where we have any number of phi's inside here, not just 2, but 3, 4, 5. It will be quite straightforward that it extends. So for our own convenience, we work with this. This is called the 2-point function for obvious reasons. It's also called the Feynman propagator that we said last time. Okay? But if I say 4-point function or 5-point function or any n-point function, it's time ordering and then that number of fields inside. These are useful building blocks to compute things like scattering amplitudes and cross sections in field theory, and this is the simplest of the building blocks. So now we have two jobs. One is express omega in terms of 0, and 2 is to express phi in terms of phi 0. Actually, this we've already done because phi is expressed in terms of phi 0 by putting u dagger and u on either side. That's why we studied u for all this time. This we already know. This one we have to do, and then we put all the information together. Okay, so to do one, let me act with e to the minus iht on the free vacuum 0. So this is how the free vacuum evolves in time with the full Hamiltonian of the system. Okay, it's the full Hamiltonian whose ground state is omega. Omega is the interacting vacuum, so it's the ground state of the full Hamiltonian. Okay, so this thing I can write by inserting a complete set of states. So let n be the eigenstates of H, so that H on n is En on n, and for n, the lowest value of n is omega. H on, this notation might be a little inconsistent, but I hope you will manage. N takes the values, let's say omega, and then 1, 2, 3, 4, 5. Because we don't want to confuse with the free vacuum. This is the interacting Hamiltonian, so this ground state is the interacting ground state, interacting vacuum, and this E naught is therefore less than all the other En for n not equal to 0. Okay, so now I can write this by inserting a complete set of states, 0 of H. Okay, because this thing is 1 by completeness, and n is 1. Now let's work out what that is. So the above thing, sum over n of course is implied, yes, thank you. Okay, so now let's evaluate that sum. The first term in the sum is e to the, okay, first of all, now that I have this, I can use the fact that H on n is En on n. So this is the sum over n, e to the minus I, Ent, n 0. I've simply used the fact that the eigenvalues of H on n are En. Now let me break up that sum to its first term and all the other terms, and we'll see that the first term is the most important. So the first term in this is e to the minus I E naught t, and what should I put here when n is its lowest value? 0 is not the correct answer. 0 symbol means the free vacuum, so omega. So omega 0. What are the remaining terms? These are terms where n is not equal to 0. E to the minus I Ent n 0. Okay, I've just broken up to the first term and all the other terms. Now, I take this factor out and I can write this omega 0 plus summation n not equal to 0 e to the minus I En minus E0 t These are all different terms with different frequencies, E naught, these are exponentials in t, so they have frequencies E naught, E1, E2, E3. So E naught is the lowest one and all the higher ones come here. So this term En minus E naught is always positive by construction. Okay. Now you see that if I take a clever limit, I can get rid of all the subsequent terms, and the limit I want is take t to, how exactly have I called it? I'll take it to infinity with a small imaginary part. Infinity into 1 minus I epsilon. That means I take it to a large numerical value times a complex number 1 minus I epsilon. Now you see over here that this minus I epsilon piece hitting this minus I gives me minus epsilon. These are all positive and this is a number that's going to infinity. So all these terms are gone compared to the leading one. So therefore we learn that this left side. So limit, let me call it now capital T. T goes to infinity 1 minus I epsilon. Advantage of calling it capital T is even if I forget to write the limit, you are supposed to think that it's a very, very large time with a small minus I epsilon in it. This on 0, which through all this became all this, then last term got dropped out, is this. So it's the limit T goes to infinity 1 minus I epsilon of e to the minus I e naught t omega times omega 0. Okay? Is this clear? I thought I just said that. And that when I take t to infinity, first of all, I don't know the value of e naught. It could have been 0 for that matter. But more to the point is, all these terms can be neglected compared to this term. Okay? If this term was also supposed to be neglected, I would find that out. And in fact, there could be very strange situations where that happens. But when I drop a term, it should always be with respect to some other term. Okay? So it's a limit. It's not that there is some time called plus infinity, but it says as I go to larger and larger times, then the importance of these terms compared to this term become less and less. So I only keep this term. What is 1 minus I epsilon? 1 minus I epsilon? What's the question? Do you know complex numbers? Okay. This is the z plane. Here's 1. Here's I. Epsilon is a small number. Okay. So this point is 1 this way and epsilon this way. Does that answer your question? Why are we taking time to be complex? That's the question? No, that isn't the question you asked. Physically mean. Okay, I'm really sorry. I misunderstood your question. It doesn't mean anything physically. It's simply a prescription how to take the time to infinity. So when we take the time to infinity, we could take it along the real axis or we could take it in some complex direction. Okay, with this prescription, we are able to get rid of these terms. That's what we want, because we don't know how to deal with all these terms. Moreover, we are looking for a relation between the state omega and the state 0. Why? Omega is the interacting vacuum, 0 is the free vacuum. Okay, and we found that relation, it's there. Okay, so it's simply to be taken as a prescription, a mathematical prescription. The infinity is very clear because it means very large time. The minus I epsilon doesn't have a physical meaning, but it tells me there's a way of taking that limit which gets rid of these terms. That's enough for me. After that, eventually, we'll see that the epsilon doesn't play very much of a role. Probably a little bit, but not very much. Okay, now what does this relation tell us? You realize that it tells me the following. This is just a number, but this is a vector, it's a state. Okay. What state is it? It's the interacting vacuum. This tells me that the interacting vacuum is proportional as a state to e to the minus IHT on the free vacuum. In other words, if I take the free vacuum and act on it with e to the minus IHT where h is the full Hamiltonian and do this for a long enough time, I'll end up in the interacting vacuum. It's a very nice simple physical statement. In other words, omega is equal to, can just solve it. Yeah, in a moment. Limit okay, I just invert this. What the statement I made now, it should be even more clear. If I take the free vacuum and evolve it for a long enough time with the full Hamiltonian, I end up with the interacting vacuum up to a normalization. Remember that normalizations are things that are inessential until I am extracting final physical results. I can even drop it on the way so long as I remember at the end to put it back. Okay? Normalization in any case is just a proportionality factor. The question is, what is the quantum state? 0 with e to the minus iht acting on it, and the answer is the interacting quantum state omega. So in fact, from this I am going to now write, which will surely make many people unhappy, that omega is in fact this, which is a very simple statement, and is the statement I made in words now. To get this statement, I simply dropped the denominator. I dropped it in the confidence that we'll put back normalizations when we get our final answer. So this solves problem 1, which is to express omega in terms of the free vacuum 0. Yes?
How do we know that omega is normalizable?
Yeah, in perturbation theory we expect it to be normalizable, and in fact we'll see very directly when we write the perturbation theory, we'll see exactly what are the terms coming from normalization and what is the effect. Yeah, another question? Yes. Yes. Yeah, they are periodic for t real, but they are not periodic if t is complex. No, the period is not 2 pi over E0. Why is the period 2 pi over E0? Yes, so it's 2 pi over that omega, which is En minus E0, not E0. Oh, the first term, yeah, okay. Yes. Yes. No, the frequency is not high. The period is high. Yeah. First of all, I'm not dropping this. I'm dropping these. That's clear? Okay. So let's see why. Yeah. I'm in the middle of answering his question. As soon as I finish, I'll answer your question. This is the limit I'm taking. Okay? You agree? Okay. So this is limit, let's say, lambda goes to infinity, real, e to the minus I, En minus E0, and t I'll substitute as lambda into 1 minus I epsilon. Alright? So let's do this. This has two terms, e to the minus I lambda, En minus E0, and e to the minus lambda epsilon, En minus E0. Now, what is the limit of this expression for fixed epsilon as lambda goes to infinity? It's the product of an oscillating term, as you said, and a term which is going to 0 as an exponential. So what's the limit? So that's the answer. Okay, now. No, that's right. Actually, you're right. I mean, we could have, but can you wait a little bit? Because what will happen is, finally we'll drop this imaginary part. We just used it as a device to get rid of these terms. Finally, we won't need it. See, what happens is, for most calculations, so there is a reason why we want the real part. We'll see that in a moment. For most calculations, the imaginary part won't play a role, so we won't write it. But if there's any calculation which subtly depends on a prescription, then we know that the prescription is that. That is the way we do things in field theory. As for the first question of yours, why we want the real part, it's because this will all go inside a time-ordered expression. I can't order times which are complex, but if the time is real and large or small, then I'm sure that the operator will be far on the left or far on the right of my product, and that's what we'll use. Yeah. There was another question here, yes.
Sir, in that expression you have written that these reform become interacting reform.
Yes.
And it takes time infinity.
Yes.
Sir, is it physically consistent? That means it never becomes interacting.
Yeah.
So, what is...
See, when we give a physical interpretation, if you find that not comfortable, you can just use the formula. See, I'm trying to derive a formula for an interacting quantity. This is a physical interpretation of the formula, which makes it easy to understand. But if you feel that a concept of infinite time is unnatural, it is unnatural physically, universe has only been there for finite time, then don't use the interpretation, but still please use the formula. It's just a way to help you understand it. Any other? Yeah. It's a mathematical trick, exactly. No, but I think their objection, valid objection is, if it's a mathematical trick, why am I giving a physical interpretation? I still think the physical interpretation is nice. But yeah, go on. But anyway, what were you saying? Okay, good. Complexifying certainly is a mathematical trick. There's no physical interpretation to complexifying time, but taking time to infinity has a physical interpretation, because it tells us that a very long time evolution of the free vacuum makes it tend closer and closer to the interacting vacuum. So it gives us a mental picture. What is the interacting vacuum? It's what the free vacuum will reach if we wait long enough when we let it evolve under the interacting theory. So one concrete application is, imagine you have a system where you turn on the interaction on one particular day. For example, in the year 0, when God said, let there be light, that is the time when H became non-zero. Okay? So now in the year 2000, you have to see whether e to the minus h times 2000 years times 0 is a close enough approximation to t goes to infinity. In practice, t never goes to infinity. In practice, actually nothing ever goes to infinity. There is no such number. But it's a very, very close approximation to say that in that case, we would be in the true vacuum today. This is why I call it a physical interpretation.
So, is this time complex valid because epsilon is being considered very small?
Yeah. Yeah, it would become quite hard to imagine what it means for larger epsilon. That's correct. You might have seen earlier that in the Feynman propagator, for example, we made the momentum complex. But that was a trick only to help us evaluate a contour integral appearing in that. So evaluate a K0 integral in terms of a contour integral. Because when you have a pole, okay, then either your contour has to go around the pole or your poles have to move so that the contour can be real. Okay. In either case, some quantity has to be complexified. So these are all to be seen as prescriptions to give a definite evaluation of something, and in case of the Feynman integral, you get time ordering only because of the way the contours cross the poles. If they crossed any other way, you wouldn't get time ordering. Time ordering is completely physical and it's all done in real time, but the contour is done in complex K. Okay, so you should think of these complexifications as some sort of intermediate step to get you an answer which involves only real time and physical system. These are all like intermediate steps. Okay, so now we have a couple of results which we can put together. So let's do it, and now the thing will rapidly simplify. So what were we trying to calculate? Omega t phi at x1. Probably in my notes I've used x and y. Good. Yeah, I've used x and y. So let's try to compute this. Oh, before that, let me make a little comment here. Everything becomes all right in the end. Okay, just one more comment. You see, this quantity, e to the minus iht on 0, can also be written e to the minus iht, e to the plus ih naught t on 0. Why? I just insert e to the I h naught t over here. Yeah, because h naught acting on 0 is 0, so this quantity is just 1. It has nothing to do with commuting with this. I didn't bring it from anywhere, I just put it there. And now what's the advantage? What is this combination equal to? U or U dagger or something? It's neither U nor U dagger, na? But it is something. It's U dagger evaluated at minus t. Check if that's correct. I claim that this is U dagger evaluated at time minus t. What was the definition of U? Yeah, I believe I've said it right. U dagger had e to the minus I h naught t on this side and e to the plus I h t on this side. So if I evaluate it at the argument minus capital T, then it's this. Good? People are very puzzled. This is very straightforward, I think. So this is even better. It says that this U operator or U dagger evolves the free vacuum, 0. I'm sorry, this I keep doing. Yeah. If I take the free vacuum and evolve it with U dagger for a long time, I get the interacting vacuum. So U and U dagger are the key objects in this study, and this is the result. Do you agree? Yes. Which left hand side? Here? Yeah. Yeah. Why doesn't it? I didn't understand. Yeah, h naught, this is 0, so this term is 1, not 0. It's e. Expand what out? No, this, yeah, each term except the leading term, right? The 1, there's 1 plus all those. 1 plus everything else is 0, that's why I put this in. But this is of course not 0 on this vacuum. Good. Nice. Yeah? Okay. So we have the following results. 1, omega is limit U dagger of minus t on 0. Now let's look at the corresponding conjugate result for this omega, because we have two omegas in this, one from that side and one from this side. This is limit t goes to infinity 1 minus I epsilon U of t 0 U of t. This is very easy to convince yourself. And now with these two facts, we can write out the quantity of interest to us. Now let's choose a particular, in order not to keep this time ordering symbol all the time, let's choose an ordering. So no, it's U of t. That's very important. He's saying if I just take the dagger, U dagger of this is U of t, but somehow it's not. Yeah. I think what we need to do is start from the first equation, which is this one, take the dagger of this equation, and then take the limit. So you need to start from the beginning. I don't know if it's easy to get this by taking the dagger of U. It should be somehow. But anyway, I'll leave this for the tutorial. But one way that you can certainly do it is start with the evolution of the free vacuum on the left with the Hamiltonian, okay, which involves a minus, right, because that is e to the minus IHT, and then convert it to this form and see what you get.
Crucial difference is going to be now you will be dealing with e to the power plus IHT.
Yes, that's true, but the question is, why doesn't that just get taken care of by the fact that U dagger of some t, if I dagger it, I should just get U of the same t. So, yeah.
The overlap only matches the overlap of 0, 0.
Yeah.
I mean, it becomes 0, 0 only.
Yes, yes. All right, I think let's leave that for that discussion. Okay. So now with all of particular time ordering, after all, how many possible time orderings are there? Either x naught is greater than y naught or y naught is greater than x naught. So we'll fix one of them and continue calculating, and later we'll come back and do the other one. So let's choose x naught greater than y naught. Okay. Then the quantity which we wish to calculate is omega phi x, phi y, omega. I don't need to write t anymore. This is equal to the limit t goes to infinity 1 minus I epsilon. In fact, I'm not going to write this limit anymore. Whenever you see the symbol capital T, just assume that it goes to infinity times 1 minus I epsilon. Okay? So this is 0 u of t. Okay. What is phi in terms of the free field? It's u dagger of x naught, phi naught of x, u of x naught, right? Okay. The next one, phi of y, is u dagger y naught, phi naught of y, u of y naught. And finally at the very end, u of minus t dagger 0. So now you can see that we have inserted all our knowledge. Our knowledge of omega as something which is evolved from the free vacuum, this omega as something similarly evolved from this free vacuum, and each of the phi's as being evolved from the interaction picture phi, which is a non-interacting, or which is a free field phi, phi naught. And the operator which does this job in every case is u. So the whole thing is made up of u's. But now it's very nice because notice that the times in this expression are all in correct time ordering. First minus infinity, then y naught, then x naught, and then plus infinity. Now you can see why we took t to be large. By taking t to be large, we can be sure that these operators in time ordering lie on either side of these ones, which are all at finite times. Okay? Good. Now, we can do the following. Okay, perhaps we have to be a little careful because remember that u dagger, although it's evaluated at x naught, it's not a local operator. So actually I withdraw that statement. I haven't yet proved that this is in correct time ordering. Okay, because u dagger contains all times from 0 up to x naught. Okay, this also contains all times from 0 up to t. So there can be overlaps of times because u is not local. U involves a time ordered exponential integral. Okay, so one more step which we've already done, and I'll put it in here, will tell us that it is correctly time ordered. The product of these two can be written as u of t and x naught. I showed you that identity, that product of u at a later time and u dagger at earlier time can be written as u of t and x naught, in which the integral is from x naught up to t. Remember the definition? This is integral from x naught up to t of h interaction. Okay, so this. Then I have phi 0. Phi 0 is a local field. So phi 0 is at a particular time x naught and space also x. Yeah. No, advertently. I will bring it back later. So the answer is that whatever I am doing is up to normalizations, which we'll see that there's a natural way to fix the normalization later. Okay. So far so good. What's the next thing? U of x0, u dagger of y0. This again by the same formula is u of x0 and y0. This is u of two arguments. It's got the integral from one argument to the later argument. Okay. Then phi of y. And finally, this with this is u of minus t and y0. Now if you look at this expression, it's all beautifully time ordered because this u involves time ordered product from minus infinity all the way to y0. Here's an operator at y0. This involves a time ordered product all the way from y0 to x0, operator at x0, time ordered product from x0 to plus infinity. Everybody is nicely in time order. I guess I made a mistake here. The definition of this and this is u from x0. What? Yeah, what was my definition? This was right? Okay. Then this is t and x0. In that case, this is y0 and x0. Look, let's have a formula. U of t1, u dagger of t2. This is equal to u of t1, t2 or t2, t1? T1, t2. So that's an unfortunate notation, but let's stick to it. Okay, fine. So t and x0. Here it is x0 and y0. And here indeed, as you said, it is y0 and minus t. Okay, so we are in business now. So whenever we see a u, we know that it goes from the second argument to the first argument leftwards. That is its job. This goes from y0 to x0 leftwards. This goes from x0 to t leftwards. So all the times in this expression are arranged in proper time ordering. Which means that this expression is the same as if I put the time ordering symbol here. Everything I put inside it. So what was my justification for this? Because it's already time ordered. So I can put in the time ordering symbol. But now that I have the time ordering symbol, I can use a very nice feature of it. When things are inside a time ordering, then their order doesn't matter anymore. Because this symbol will take care of the order. So I can move them around as much as I like inside. Okay, now if I move them around, I can in particular put phi naught of x and phi naught of y first. Okay, what else do I have? Now I break these back into their constituent pieces. So this is u of t. Okay, then I have u dagger, okay, I have u dagger of minus t. Then I have u of, from here I have u dagger of x0, from here I have u of x0, u dagger of y0, u of y0. You just collect them all. Okay, now what can I say about this pair? It's 1. And this pair, sorry, maybe I wrote it wrong. Probably this is the correct order. U dagger. It doesn't matter because finally it's 1. Sorry, maybe I wrote both wrong. Let's start again. What's the first? Is this, right? Which comes out daggered. So u dagger x0. U x0, u dagger y0, u y0, all inside time ordering and 0. So now I can in fact notice that this is 1 and this is 1. Okay? And the only thing I'm left with is this factor. So you see that the quantity I want to calculate up to the normalization, which I still have to put back, is the corresponding free quantity times a very, very non-trivial factor depending on u. And u is the key object which depends on the interaction Hamiltonian exponentially. Okay? So I can collect this and write it as 0 t of phi naught x phi naught y. Now again I can use the formula for u of t, u dagger of minus t, and it is time ordered e to the minus I minus t to t h interaction Hamiltonian t prime dt prime 0. Time ordering is outside, therefore I don't need to take it. Exactly right. That would be the next step. I would drop it, saying that since time ordering is outside, I don't need it anymore. Very good. So this is more or less our final answer. And there's only one thing to come back and fix. Sorry? What? Yeah. The limit is understood. Okay. So this limit is nothing but minus to plus infinity. Okay. That's all. So we can perhaps drop this t, or we can always remember that t goes to infinity 1 minus epsilon, which means effectively it's minus to plus infinity. Okay. So it's like the action corresponding to the interaction Hamiltonian. We just integrate it over all time. Okay. If there's ever any subtlety, then we'll remember that this was the prescription for that subtlety. Now, the only thing we've not done is to put the normalization, and it's extremely beautiful. And this again I won't do in any detail, but you can convince yourself that normalization is taken care of by dividing by the same expression but without any fields phi at x, phi at y, just so therefore, the final big answer is that 0 t, in fact now I am going to generalize it to an endpoint function, is equal to 0 t of phi naught and this is the master formula for all of perturbation theory in quantum field theory. At least I think all the terms are quite easy to understand. What it says is that the n point function, vacuum expectation value of product of n fields inside time ordering, is equal to the same quantity in free field theory modified by an exponential of the interaction and divided out by just identity in place of these operators modified by the exponential of the interaction. Okay, and now you just have to go ahead and compute two things just to fill in, and then I'll stop. First of all, I didn't actually go through the case where the time ordering was the reverse one. I only assumed x naught greater than y naught. But if you assume y naught greater, since you got the answer to be time ordered, if you assume the other way, you would also get the same answer. So it's easy to convince yourself that whichever time ordering you start with, the end answer is the same. And so this theorem is actually correct. And second thing to notice is that H interaction picture goes like lambda. In fact, what is H interaction picture? Remember that H int was lambda phi to the fourth integral d3x. Okay. Now H interaction picture is obtained by sandwiching this between e to the I h naught t and e to the minus I h naught t. So it's lambda by 4 factorial integral of phi t n x, phi naught of t n x to the fourth d3x. And after d3x, there's also an integral in dt. So finally, it will just be integral over d4x of this thing. Right? Because the field phi at a fixed time t equals 0 evolves into this under the free Hamiltonian. So now you can see very explicitly that the expression on the right hand side only depends on phi naught. All kinds of complicated functions of phi naught. Here they are just phi naughts, and here there are phi naughts, here there are phi naughts. Okay, so all the calculations have to be done only with phi naughts sitting between the free vacuum and the free vacuum. Okay, and finally, what happens when lambda is 0? When lambda is 0, this term disappears, this term denominator is 1, and we get the free field endpoint function. So of course the interacting one reduces to the free field one, so all is good. When lambda is non-zero but small, it will still be true up to corrections. That means when we calculate the right side, the lowest order term in lambda will be the term that we get by putting lambda equals 0. The next order term will come by expanding either this or this to first order. Then the next order will come by expanding this to second order or this to second order or each of them to first order, like that. And we'll do this kind of thing next time, but it's very, very important to remember that when you do a calculation, you should first decide what order you are going to. Okay? Otherwise you can easily make mistakes. If you are working to order lambda, then you have identities like 1 minus lambda into 1 plus lambda is equal to 1, not 1 minus lambda squared. If you are working to order lambda, then this is a correct identity. If you are working to order lambda squared, you must make sure that all your factors are taken to order lambda squared and the answer is also taken to order lambda squared. People often make this mistake to work to some order and then insist on keeping the next order term, where you have dropped something which you didn't remember and you are keeping some other terms, and you get inconsistent answers. So you should be very careful in perturbation theory to fix the order of your expansion and work only to that order. Okay, and finally all these calculations are in the notes which are up on the web. And for tutorials, the problems, I think most interesting ones would be to justify the expression of u as a time-ordered exponential integral, and to understand why the in vacuum and out vacuum, as they are called, this omega and this omega, are given by u dagger of minus t and u of plus t rather than both at plus t or both at minus t. Okay.